The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good afternoon, everyone. I'd like to welcome you to my presentation today, which is titled Concentric and Eccentric Behavior of Rectangular Columns Confined by Steel Ties and FRP Wrapping. I'll start with the outline of my presentation. I'll begin with listing the objectives and then give a brief introduction about the topic, discuss the formulation that we utilized in order to obtain our results, and then talk briefly about the computer program that was developed using our proposed approach, list and discuss the results that we obtained, and finally end with the summary and conclusions. So our main objectives are to evaluate our proposed model, which combines the effect of steel and FRP confinement in rectangular concrete columns. And from that model, we can use it and generate interaction diagrams for these columns, accounting for the confinement effect in them. So there were many models that were proposed for FRP confinement effect in order to describe it in concrete columns, and the most popular one and accepted one is lamenting model, which was actually chosen to be the most suitable model by the ACI Committee 440. And as we know, the columns, the reinforced concrete columns with FRP wrapping are under the effect of two lateral pressures. In the cover, we have the FRP pressure only, while in the core, we have the combined steel and FRP pressures working together to increase the strength of the concrete in the core. So in this study, we're going to propose a new model that combines the effect of these two pressures and account for them. So the formulation consists of the following. First, I'll go quickly over the generalized moment of area theorem, and then talk about the material models used, which include Mander model for steel confinement and lamenting model for FRP confinement. And then I'll go over the combined confinement model, which combines the steel and FRP from the two previous models, talk about the eccentricity-based model that we used to get the interaction diagrams, and finally go over the confined analysis procedure that we followed. So we started first with the general equation for the axial strain for a column that's under biaxial bending and axial load, which was obtained by Hardy-Cross in 1930. So using this equation, in order to obtain the axial strain, we have to divide by the modulus of elasticity, as shown in the second equation. And from the linear strain distribution, we can obtain the curvatures in both x and y, as shown in equation 3. And these two equations for phi x and phi y, and substituting back in these values in epsilon z equation, we obtain this simplified equation for the axial strain. And if we substitute with the values at our geometric centroid, which is located at y bar and x bar, and then solve for the axial load there, we obtain this equation. And we will refer to the EA y bar value as the moment of the moment about the x-axis of axial rigidity. The same thing for the y-axis. So these two are cross sections along the y-axis and x-axis, and they show G refers to the geometric centroid, C refers to the inelastic centroid. So in the first two equations, we are finding mx bar. Mx bar refers to the moment at the geometric centroid. So we are transferring the moment from the inelastic centroid to the geometric centroid according to this equation for both x and y. And we know that mx, which is at the inelastic centroid, is obtained from the curvatures that we calculate according to the previous two equations for phi x and phi y. And then substituting back with mx in this equation and p from the previous equation for the axial load, we are able to obtain this expression for mx bar and my bar, which are the moments about the geometric centroid. So we are demonstrating the equations now in matrix form, and this matrix relates the axial load and moments about the geometric centroids, the bending moments, with the axial strain and the curvatures with x and y. And if we transfer these moments back to the inelastic centroid, we are able to cancel these terms, which are the moment about, of axial rigidity about x and y, because we know these to be 0 about the inelastic centroid. And this effect helps us to decouple the moments, the bending moments, from the axial force, and we can easily find each of them separately. Moving on to the material models, starting with Mander model for steel confinement. Mander assumed that this pressure distribution within the core, this is at a tie level, and this is between two consecutive ties. And he assumed that we have the effective area is basically the confined core area after deducting the parabolas between the consecutive longitudinal bars. This is how he formulated his model. So, and in order to obtain a factor that reduces the total confined area to the effective confined area, we have this coefficient, which is the confinement coefficient, which accounts for the spacing between the ties and the spacing between the bars in this equation. We can also obtain the transverse reinforcement ratios, rho x and rho y, from these equations. And then if we substitute back in these two equations, knowing the yield stress of the hoops, we are able to obtain the lateral pressures FLX and FLY along X and Y, which are basically the pressures that are confining the concrete and helping increase its capacity. So here we show the stress-strain diagram based on Mander model for confined concrete. Compared to the unconfined concrete, we see a big increase from an increase from F prime C to the confined strength, which is FCC. And this equation here helps us to find the stress at any strain level, substituting for the strain and to obtain X and then R, we are able to find FC. We're also able to find epsilon CC, which is the strain at the strength, using this formula. So these formulas help us to find the stress at any strain level for our concrete. Moving on to Lamenting model, which is used for FRP confinement. This model has two regions that are both ascending. Mander had an ascending region in the beginning and a descending region here, while Lamenting has two ascending branches, basically. So for that case, we have two separate equations to calculate the stress given the strain level. So we have this equation for this region, and this equation for this part of the stress-strain diagram. And we need these all parameters in order to model it. We can obtain the slope of the second branch here using this expression, the strain at which the two equations change using this equation, and then the ultimate strain here is obtained from this equation and is limited by ACI to 0.01. So in case that we obtain a strain that's higher than 0.01, we have to limit it to 0.01 and use the E2 value that we calculated to obtain a lower FCC, because we have to meet this requirement. And then we obtain the lateral pressures using these expressions for the FRP. So now I'll move on to our combined confinement model, which combines both steel and FRP. We have two cases here. We have the case for the cover, which is the first case. The cover is only under the effect of FRP confinement. And the pressures in this case are in X and Y are calculated according to these two equations, and they are just for they just depend on FRP. While for the concrete core, which is confined by both FRP and the steel ties, we'll have two elements in the lateral pressure equation. The first comes from the FRP, and the second term comes from the steel pressure. For Lamenting model, in order to be able to use this model and confirm that the ascending branch continues upward and doesn't go down, we need to verify our lateral pressure to the unconfined compressive strength of the concrete. And for that, we need to obtain FLF in general for the section. According to Lamenting, we have to define a circular section that's equivalent to our rectangular section. We obtain the diameter of that circle using this equation by taking the summation of the squares of the dimensions of our rectangle and taking the square root of that. And then we substitute back in this equation to obtain the lateral pressure. This pressure is then divided by the compressive strength of the unconfined concrete to get this ratio. According to ACI, we need to confirm that the ratio is greater than 0.08 in order to use Lamenting. Otherwise, we go ahead and use Mander model if the ratio is less than 0.08, which means that the FRP confinement is not enough to ensure that the second branch of the Lamenting equation is ascending. So this shows the procedure that we use to obtain the FCC, the confined strength, FCC. This uses a multi-axial analysis approach for which we determine first FLX and FLY as explained earlier. We designate these two as our major and intermediate principal stresses, and then we assume a value in the beginning for our FCC. This will be our minor principal stress, sigma 3. So we go ahead then and calculate the octahedral normal stress and shear stresses, and also the load angle theta using these expressions. After doing that, we are able to determine the ultimate stress meridian surfaces TNC, which using these equations, which were provided by Elway and Murray in 1979. And for these equations, we need to determine the normalized octahedral normal stress, which is obtained by dividing the stress by the unconfined compressive strength of the concrete. So after that, we go ahead and use the interpolation functions that were derived by Willem and Warwick in 1975. Using these functions, we are able to obtain tau octahedral bar and denormalize it to get tau octahedral. And now using this new value, we go ahead and compute sigma 3 back again from this expression. We substitute back and get sigma 3 now and check the value compared with our assumed initial value of FCC. If they are the same, then we obtained our FCC. If not, we use this new value and repeat the process until we converge. So now that we have our FCC, which is for the confined case, we need to go ahead and work on the eccentric model. Both Mander and Lamenting models work with concrete that's under concentric load. So this works with fully effective confinement, basically. But in eccentric cases where the load is, where we have an eccentricity and the load is not at the centroid of the section, we won't have the full confinement effect involved. And this is why we needed to define some parameter that helps us decrease the effect of confinement and obtain a stress strain diagram that's between the unconfined and the confined curves. So we started by generating some graphs that models that we calculated the compression area to the total area ratio in the section, given using the normalized eccentricities for columns with different aspect ratios. And we plotted all of these data points in one graph and tried to fit a curve to it. And this is the equation that we obtained. So now using this equation, we are able to obtain the compression ratio parameter given the eccentricity and the rectangular section dimensions. So now we can go ahead and use this equation to find a curve that's between the confined concrete curve and the unconfined concrete curve, which represents the eccentric case that we have. In this case, for example, in general, we have an infinite number of curves between the confined concrete and unconfined concrete curves, but using that parameter, we'll obtain a specific curve that represents the level of eccentricity involved. So this shows the graphs for Mander, and here are the equations that we use. This is the main equation that from which we obtain the new FCC bar, which is the eccentric strength of the concrete, and is based on the CR parameter that we calculate from the eccentricity. After that, we use the previously defined equations in order to calculate all the other parameters that we need to plot the Mander curve as shown here. Similarly, for lamenting, we have also infinite curves in between the confined and unconfined cases, and we are going to use the CR parameter again to calculate FCC bar, and then use this FCC bar value to calculate all the other parameters needed to obtain the stresses along this new eccentric curve. So finally, here is the flowchart that shows the procedure for the confined analysis. We start with calculating the initial section properties of our section, and then providing an axial load, eccentricity, and alpha angle. The alpha angle relates the moments, which it's basically tan alpha is equal to my divided by mx. So it's the angle between the resultant moment and the moment about the x-axis. And then we start our procedure. We transfer our moments to the inelastic centroid using these equations. We then calculate the curvatures and the strains for the linear strain distribution. And then from that, we are able to divide our section using the fiber method. We divide it into multiple filaments and then calculate the strains and stresses for each filament in our cross-section. So from here, we go ahead and compute the new section properties based on the strains that we obtained. And then after that, we are able to calculate the moments and axial loads using the equations that were demonstrated at the beginning of the presentation. When we are done, we go ahead and transfer the moment back to the geometric centroid. We check if our inelastic centroid, our assumption for the inelastic centroid was correct. We check if we converge. If not, we go ahead and calculate a new values for the centroid and repeat. If yes, we go and check our forces and bending moments convergence, internal versus external, which will definitely converge if the previous step is accomplished. And after we are done with this step, we now have our section and we know the strain levels there. We have to compute and we have to compare our strains with the limit strains for both steel and concrete to decide whether our section failed or not. So we compare steel with the 0.05 and the concrete with the crushing strain of 0.003. If we don't reach any of these limits, this means that the section hasn't failed yet, and we increase the load and repeat the process again. If we exceed any of these limits, this means that we have reached a failure surface, and we record the P and moment values obtained, which this will be a point on our interaction diagram. From that, we go ahead and get a new eccentricity, recalculate everything. This will give us another point on this interaction diagram, and so on until we are done with the eccentricities. Then we provide a new alpha angles. This will give us other interaction diagrams. So our alpha will vary between 0 and 90. So we'll get the 3D surface that's for different bending moment combinations, mx and my. So this is a screenshot of the computer software K.Column Expert that was developed and we had our approach implemented in it. The user can input the data here, the geometric properties, the concrete properties, and the steel properties. The user can also specify whether we have FRP in there or not, and then choose which curve to plot. We can plot confined and unconfined curves, interaction diagrams here, and the user can also provide specific points to check where they lie on the graph to make sure that whether the column has failed or not, depending on our interaction diagrams here. So moving on to the results, we used our program and we compiled a database from the literature. We used the database compiled by Roca and his co-authors. And also we used some specimens that were compiled by Darby. Starting with the first specimens that were tested by Bosias. This specimen didn't have FRP in it, so it's just under steel confinement. And here are the section properties for it. This is the cross-section. And this shows the interaction diagram that we generated using our procedure and program. And this is the experimental point here. And it's outside of the diagram. So in this case, our diagram is conservative. Moving on to the next data point here. In this case, we have 2 plies of CFRP wrapping around the column. And here the result is also outside the interaction diagram, which shows that we are conservative again in this case. Next, we have instead 5 plies for the specimen, and again the point is further away, so we are even more conservative in this case. In this last one, we have 5 plies of GFRP, and we can again see that the point is outside the interaction diagram. The next 4 specimens are the same as the first 4, but the only difference is that they were tested in the weak direction. And again, the first one has just a steel, and we're conservative in all of them. This has 2 plies of CFRP, this one has 5 of CFRP, and this one has 5 GFRP plies. Then we have a few specimens that were tested by Memun and Sheikh, and the first one again is just with the steel. This one this time is inside our interaction diagram, however it's very close. The next specimen had 2 plies of GFRP, and we're conservative in this case. This one has 4 plies of GFRP, and it's inside but very close to the curve. This one has 2 plies, and it's also very close to our curve. And then we have this one with just 1 ply of GFRP, and it's outside, so we're conservative. This one is also outside the curve. And then we have 4 more specimens by Harajli and Dertail. This one has just a steel. We're conservative in this case. This case also even with FRP, with 1 ply of FRP, CFRP. This case is with steel only. And this is with FRP, 1 ply of FRP. The last 2 specimens were tested by Darby, and this one has 4 plies of FRP. The point in this case is inside, but it's close to our analysis results. This one is a bit further away, but it's inside the curve. So now, in conclusion, in this work we were able to create a model that combines the FRP and steel confinement effects in rectangular reinforced concrete columns. And the approach that we developed was implemented in the computer software K.Column Expert and used to plot interaction diagrams. And as shown in the results section, the proposed model provided us with good agreement with the experimental results, and in many cases our interaction diagrams were conservative. So this concludes my presentation. I'll be glad to answer any of your questions.